This is an applications presentation of laser shearography being used in Marine NDT for the inspection of yacht hulls and rudders. Here is an overview of Marine NDT applications used with laser shearography. As can be seen, most applications are of sandwich or honeycomb components. In the case of laser shearography, the technology is well suited for the inspection and detection of disbonding, cracked and crushed cores, and no bond splits that can originate between the skin and the core of the material. Application A is a glass fiber reinforced plastic skin laminate material with a double foam core sandwich. In Figure 1, we see a cross-section image of the two panels being inspected, P1 and P2. Figure 2 is an image of the sample to be inspected from the top. The surface was sprayed with developer, and the test object size is approximately 310 by 310 millimeters. Using thermal excitation, specifically two 1000 watt halogen spot heat lamps, heat was applied for a duration of 12 seconds, requiring then after 8 seconds worth of measurements. The entire inspection required only 20 seconds, yielding an inspection rate of 0.3 meters squared per minute. Using the same measurement procedure with a shearing angle of 0 degrees and 45 degrees in the left and in the right image, we can see the detection of multiple indications. Performing the same test again on P1, using vacuum ambient excitation, a following pressure differential of 10 kilopascals in the left image and 20 kilopascals in the right image indicate slimmer presence of defects. The duration of inspection using vacuum ambient excitation only requires 5 seconds. Here is a video of phase map for the vacuum excitation application to panel 1 from 0 kilopascals to 20 kilopascals. On the right we see the indication of multiple defects. Figures A and B indicate node splits. Figure C indicates impact damage, specifically being a crushed core or possibly a disbond. D is an indication of a disbond within a stiffened structure inside the element. And E and F are both indications of disbonding. In sample P2, we use thermal excitation, specifically two 1000 watt halogen spot heat lamps. Heat was applied for 12 seconds. Here is a phase map of the thermal excitation application to P2. We see indications here in the center and also on the right side as well. Using vacuum ambient excitation with a pressure differential of 10 kilopascals and 20 kilopascals, it is quite clear that there are more defects and also stiffened structures beneath the component surface. Here is a video of the phase map of vacuum excitation application to P2 from 0 kilopascals to 20 kilopascals. We can see 6 indications. A and B are indications of impact damage, either a crushed core or a disbond. C is an indication of erosion damage. D is an indication of a disbond inside a stiffened structure. And E, F and G are all cases of disbonding. Application B is a CFRP skin laminate foam core sandwich component. The test object size is 30 centimeters by 42 centimeters by 4.5 centimeters. Here is a live video recording of thermal excitation application using a Floor Explorer with thermal excitation. Here we can see the live phase map visualization. Using two 1.3 kilowatt halogen spot heat lamps, heat was applied to the test object for 10 seconds. A reference image was applied then at 15 seconds, and snapshot images were continuously taken up to 30 seconds. We can see the clear indications here inside the phase map. Using heat application on the left for 10 seconds and heat application on the right for 15 seconds, using a shear of 2.5 and 5 mm shearing, we can see the presence of 5 indications. Application C is a carbon fiber reinforced plastic laminate skin foam core sandwich material. The test object size is 27 by 50 by 4.5 centimeters. We can see in figure 1 an image of the sample to be inspected with sections 1 and 2 marked. Here is an image of the sample from the top and a cross-section image of the sample here. Here is a live recording of thermal excitation application using a Floor Explorer with thermal excitation on section 2 of the panel with live phase map visualization. 2 1.3 kilowatt halogen spot lamps applied heat for a duration of 10 seconds. At 15 seconds, a reference image was acquired, and that snapshot images were acquired at 1 per second up to 25 seconds. Comparing thermal excitation being used for 10 seconds and thermal excitation being used for 15 seconds with 2 different shear settings, we see that there are 2 major defects present in both images, on the left side S2 but also on the right side S1. Application D is a glass fiber reinforced plastic laminate skin with foam core sandwich and a GFRP integral stiffener backing. The test object size is 45 by 17 by 3 centimeters. Here we see a vacuum excitation application on section 1 of the panel with live phase map visualization. The pressure is changed from 0 to 5 to 10, then back to 0 kilopascals again. We can see the internal integral stiffener design of the panel. The duration of this inspection required only 10 seconds. Applying another reference step, going back to 0 kilopascals, we see the defects inside the panel. Using a shear distance of 5 mm and a pressure differential of 5 kilopascals for the top and 10 kilopascals for the bottom, we see the same indications in both measurements. The vertical lines actually indicate incisions made in the side and in the middle of the component. Application E is a carbon fiber reinforced plastic laminate skin with Aramid honeycomb sandwich. The test object size is 55 by 40 by 3.5 centimeters. Figure 1, we see an image of the sample to be inspected from the side. Figures 2 and 3 are images from the sample to be inspected from the top and from the bottom. We can see very clearly there is a cutout at the back of the sample. Here is a comparison of vacuum and excitation on the sample section of panel with a live phase map visualization. On the left we have vacuum ambient excitation where we go from 0 to 5 to 10 kilopascals, and on the right we use thermal excitation with 2 1.3 kilowatt halogen spot lamps with 10 seconds of application heating. This is of exactly the same section. We can see that there is a very large disbond in the right part of the sample. We can also see the cutout here, which is very clear in the vacuum ambient excitation. Using vacuum ambient excitation with a shear setting of 2.5 mm and 5 mm with a pressure differential of 5 and 10 kilopascals, we can see the presence of 1, 2, and 3 indications. Application F is a reference panel, specifically aluminium skin with aluminium honeycomb. The top aluminium skin is 1 mm and the honeycomb is 13 mm in thickness. The test object size is 37.5 cm by 29 cm by 1.5 cm. In Figure 2, we see an image of the sample to be inspected from the rear. There are multiple cutouts. On the top line, there are line cutouts, square cutouts, circular cutouts, and half the thickness from the top line, also of line cutouts. In video 1, we see vacuum excitation being applied to the panel. The vacuum excitation is from 0 kilopascals to 5 to 10 back to 0 kilopascals again. The duration of inspection takes approximately 10 seconds. It is visible to see where there's entrapped cells within inside the honeycomb sample, in that the entrapped cells actually cause minor changes in the bending stiffness. Where there is a cutout actually indicates that there is no entrapped cells behind the sample whatsoever. All the defects using vacuum excitation are as such visible. Using shear distances of 2.5 mm on the top and 5 mm on the bottom, and performing the measurement at 5 kilopascals pressure differential on the left and 10 kilopascals pressure difference on the right, we see a doubling of the fringe intensity from here to here to here, or from here to here to here. Application G is a contract measurement performed on the hull of a yacht. Using vacuum partial excitation, the skin to core disbond was initiated here at this particular location. The defect propagated further due to fatigue stresses from sailing along the waterline, all the way up to here. This is the phase map of the ending defect indication. The total length of disbonding was 3.1 meters. Application H is a rudder contract measurement investigation of the bondline. Using mechanical and also vacuum partial excitation, verification of the core to skin bondline on a racing yacht was performed using the Q810 system pictured here. Mechanical bending tests were conducted under various loading regimes, indicating localized bondline detachment, presented here in this phase map. Here is an overview of further Marine NDT applications used with laser shearography. Application I is an aluminium skin double foam core sandwich, and application J is a carbon fiber reinforced plastic skin foam core sandwich material. Application I is a aluminium skin double hard foam core bonded sandwich component. The surface was sprayed with developer. Figures 1 and 2 show an image of the sample to be inspected from the top. In Figure 3, we see a cross-section image of the sample to be inspected with the double hard foam bonded core. The test object size was 100 by 50 by 7 centimeters. Using vacuum ambient or vacuum partial excitation with a pressure differential from 0 to 20 kilopascals, the duration of this inspection required only 6 seconds. Section 1 of the panel resulted in quite obvious large defects. Section 2 and Section 3 also had very large cases of disbonding as well. Here we see a video excitation of Section 3 of the panel with live phase map visualization. As we can see, there is considerable indications here. Application J was a carbon fiber reinforced plastic skin laminate with a foam core sandwich. The surface was sprayed also with developer. The top laminate CFRP skin was 5mm in thickness, and the middle foam core was 60mm in thickness. The test object size was 119 by 52 by 7 cm. In Figure 1 we see an image of the sample to be inspected with the pink indication area of complete disattachment. Using vacuum ambient or vacuum partial excitation from 0 to 10 kilopascals, we can see very clear disattachment with inside the pink border. Using also thermal excitation with heat application for 10 seconds, it is also very clear to see the disattachment in the panel with inside the pink border as well. Thank you for your attention. If you have any questions or comments regarding the applications of Laser Shearography NDT, please contact Dantec Dynamics.